Now we begin the second lecture of the event. It's a great pleasure to introduce our speaker in data-driven plant breeding, Professor Alencar Xavier. Professor Alencar holds a bachelor degree in agronomy from Federal University of Santa Maria and a PhD in plant breeding and statistical genetics from Purdue University. He began his career at the multinational Corteva AgriScience as a quantitative genetic and currently holds the position of breeding analysis. Additionally, he is an adjunct professor at Purdue University. Today, Professor Xavier will present leverage correlated information under multivariate setting. Please join me in giving a warm welcome to Professor Xavier.
All right, thank you everyone. It's a great pleasure being here, and I understand that I'm the person holding you from just going home. It's the very last lecture of the day, and I'm sure you're all tired. So I'll try to take it easy as easy as I can. It might be a little technical talk. When I was invited, I was between giving a more of a high-level talk or maybe a more technical, and my understanding is that this event is held by people with a plant breeding background, and mixed model is something that takes a big chunk of your background on doing the analysis, or quantitative genetics has this basis on Gaussian theory. So maybe understanding alternative ways to solve this mixed model and leveraging information that it can provide can be beneficial. So here's a brief overview of my talk today. I'll give the rationale of why we are doing this study, and I'll pass through how we could estimate coefficients in a mixed model equation using the univariate or multivariate model, the variance components, and some results I got out of a simulation. And on the right, I'm just pointing to the paper that is describing most of the techniques being presented in this presentation. We have a follow-up paper that's about to be published, but I was not as lucky as Lipka, who got the paper accepted on Saturday. Mine has not quite yet been accepted. It got all those minor reviews and all, but I promised them if the paper had been accepted up to 3 p.m. today, I would give you a new presentation. So that did not happen. All right. So as per the introductory part. So I guess maybe I could straight up skip this one because you guys had this amazing talks yesterday and the workshops today that capitalize on the use of genomic prediction when and where that's utilized, so we can use for multiple purposes. Here I'm just reiterating what previous speakers mentioned. You can imagine that it's just a simple prediction technique. You have individuals that have phenotypes and genotypes, individuals that have only genotypes, and then you can predict the phenotype. It's basically a simple regression setting. So the rationale for deploying a multivariate goes as follows. We know that there are good techniques that are deployed for genomic prediction. Here I'm just mentioning two that you may have heard of. The classical GBLUP, base B. And one thing to consider is that the phenotypes we collect, they can come from a wide range of places. There are many phenotypes, and if you recall in our classic Falconer quantitative genetics, one may call that the same phenotype collected from two separate places may be characterized as two correlated traits. And exploring and understanding that correlation is a key component of how we take decisions in plant breeding. All right, so why would you do any multivariate? One, depending on what type of model you run, you can either get the G/E patterns if you do a multi-environment trial, or you can understand the correlation among traits if you run a multi-trait model. Either way, you get higher accuracy. We know that we are living in this era of phenomic traits with a lot of emerging traits being collected from drones and rovers and satellites. One thing that multivariate plays a key role there is to provide an estimator of the genetic correlation between this new trait you are assessing and yield. However, one big problem of multivariate models is that it's often computationally prohibitive. So basically, for every one trait you add into the model, it increases in k exponential 7 the computational time of it. And I will propose a new solver today. And just to get it out of the way, because I know that people just trying to remember the first 3 slides, my third slide here is one implementation that we have that gives you like the bulk of what I'm trying to convey today. If you imagine that you start from a data set on the left where you have genotypes as rows, traits as column, a multivariate model will fit the genomic model for all the traits at the same time. They will give you the statistics you'd get either way, which are the heritabilities, marker effects, breeding values, as well as the genetic correlation, which is the piece of information we are getting extra from running those multivariate models. All right, and how do we use, or why would you care about those correlations? As I mentioned earlier, you can use that information to do some very cool things. On the left is a study that I published in 2014, where we used the correlation between among 14 soybean traits to infer a causative network of how grain yield comes to be. So if I was to improve yield, what are the traits that are directly connected to yield? On the right is an example on the G by E basis, where each band that you see there, the little balls, correspond to a multi-year BLUP for that region. And what we did, we ran a model with those, 70 little bins. So we fitted 70 traits at the same time in a multivariate settings. We used the genetic correlations to get a hierarchical clustering to do some sort of environmental classification based off not on environmental covariates here, but on the genetic correlations among locations. So even though we did not tell the model which locations are close to each other, just the genetic correlations were able to identify which regions are more similar to one another. All right, so what exactly does a multivariate model mean, and why would that be any better? So you can imagine the regular model, the simplest you can get is your phenotype Y is equals to your genetics G plus your residuals E. And if you model them from the perspective of what is the expected variance of those two traits if being modeled together, you see that they have the variance of any of the two Y's is not a vector, it's a matrix. And what you see in blue there is the sigma A is the genetic covariance between trait 1 and 2, and the sigma E is the residual covariance between traits 1 and 2. Those covariances you only get if you run a multivariate model. Granted that there are some approximations, perhaps you can infer those from a compound symmetry, but the exact correlation, the covariance, it's best estimated or most reliably estimated through a multivariate model. And another thing tying that same thing with a G by E model, you can imagine that for every 2 environments, there is a correlation between those 2 environments that is in part due to genetics. And that's exactly, again, the information that you'll be getting from the sigma A. And I don't want to overextend and explain the formulas, but you can imagine that on the very bottom, when I do the same model in matrix notation, the first line, G1, it would be the solution for the breeding values of trait 1 goes to up to a certain point. The bivariate, it goes to the same point and some extra things highlighted in yellow. So all that chunk in yellow is the piece of the formula that you get by running a multivariate. So we can mathematically express the gains in information just by the difference in the conditional expectation G1 or G1 given G2. All right. So one thing that the method we are proposing does is to fit not as a GBLUP using genomic relationship, but we fit as a ridge regression, meaning that instead of getting the relationship map, we mapped the SNPs and calculate SNP effects. So sometimes referred to as a sniplop. And why would you do that? So basically, regression type models, you can just store the marker effects, and every time you want to make a new prediction, you don't have to rerun anything. You just multiply the effects and you get those GBVs. It's comparable to what we call sometimes as a multi-stage framework, where you first get blues and then blobs, and then from the blobs you get the GBVs. Another thing is well-known properties. It works just like a GBLUP. It is Gaussian, it's additive, and has all those nice known properties. The added benefit is that we do not have to create or invert a G matrix, which is not always positive definite. So every time that you have more individuals than markers, G will not be positive definite. And another thing is that as we are going to calculate those as a multivariate, we still get all those nice variance covariance estimates that we get to estimate heritability, reliability, etc. All right. So as I mentioned, we are going to start the presentation with a very brief description of what the model would look like. That would be a ridge regression model. Mu is the overall mean, Z is the marker information, beta marker effects, and then the residuals. As we are working in a multivariate framework, Y is not one phenotype, but the stack of the phenotypes, and so on. And Z is a block diagonal of those Z matrices, because we are modeling not only one trait at a time, but not one trait, but multiple traits at the same time. And then our sigma now is actually a matrix containing all those variances and covariances. All right? So the corresponding mixed model equation to that would be huge. Because say that you have a few thousand markers, and then you have the chronicle of that, which means that blows the dimension and is a big and dense matrix. Not only that, depending on how you estimate the variance components, you have to invert the whole shebang. And even if you store just half of it in memory, still it's a big stuff. And personally, the motivation why I want to get away from that is because I ran all my analysis in the PhD using just a Walmart computer that did not have a lot of computing power. When I started working in industry, they gave me the worst computer because I was an intern, and they said that if you're a good programmer, you can do whatever in this crappy computer, as an excuse of why give the intern a crappy computer. So long story short, was a huge matrix that would have to be inverted, and that would jeopardize all the internship that I would never be able to get anything done. All right, so the conclusion from that previous slide is that computing those multivariate models with a bunch of traits is basically impossible. And that's how not having money to buy a new computer gets in. All right, so I'm going to briefly recap now how coefficients are estimated these days, because we do not build C matrices. If you think of packages that were mentioned earlier today, BGLR, they are all based in something called the Gauss-Seidel. And I'll start with the univariate, and then I'll jump into the multivariate. So the way how it works is very simple. I fit one marker at a time. I take the residual, I fit the next. I take the residual, I fit the next. So my whole genomic prediction is done in cycles, where all my operations are not in matrices anymore, are just vectors. So I just estimate one effect at a time. Sometimes they call those coordinate descent in machine learning, but in breeding we refer to as the Gauss-Seidel. So basically, because we are feeding one at a time, we don't have to even bother building those big matrices. And as you can see on the animation on the right, eventually the model, after a few iterations, it will converge. And on the right, you see how the fitted values come together. So the multivariate counterpart looks about the same, except in matrix notation. It is a small system of equation. It's a trait by trait. So if you have only one trait, you're just dealing with vectors. If you have two, it's a 2 by 2. The paper tells you some ways how you can even avoid that system of equation. You can get even smaller. But for the purpose of this presentation, I'm just saying this formula is basically the same one as before. Oops, the same one as this first one, but in matrix notation. Cool thing, we moved things around so that we don't have to do any Kronecker. I know that it doesn't mean much to you guys, but 2 years ago when I gave this presentation in Illinois and I said no Kronecker, Ed Buckler jumped from the seat. That was, sure, one person reacted, but it was good enough. I was happy. That does mean something to some people. All right, so the big selling point is no Kronecker. No need for blowing the dimension of the matrices. Because again, we're gonna be fitting one marker at a time, take the residuals, fit the next. And that's the system of equations that we stored. It's the same little chunk of equations we saw earlier. And what you can see here, I color by things that we calculated only once, things that we calculated in every iteration or for every marker. So basically, some of the z prime z, which is just the Liouville frequencies, we do it only once. The estimation of the variances is one every iteration. So you finish doing all the markers and then you update once the variance components. And then in red is what you do for every marker. It's tiny. I mean, really, on your memory, if you have enough memory to load your data, you probably have enough memory to run this model because it does not have much overhead on it. And the whole magic happens just because of this one value here, the one covariance that we have been talking about since the previous slide. Another thing that this one we did borrow from the machine learning literature. We usually used to update the markers in order. And it will take, here on the right you can see, up to 3,000 iterations until you get like a good convergence. When you update the markers in random order, you know, it sounds silly, but just to randomize the order of the markers, the same model converged in 50 iterations, which is pretty insane. I mean, the cost of those iterations is about the same cost as when you run those BGLR packages, MCMC, but someone would laugh at your face if you tell them that you ran only 50 iterations. Because for MCMC, that is not enough. But again, this one, it converges to the point, not dances around the response like MCMC. Fine. Gauss-Seidel is an old methodology. It's been around since the 30s. Maybe most of us knew about. But what about the variances? The reason why people use Gauss-Seidel sometimes is because Gauss-Seidel does not give you variance components. So to jump into the variances, I decided to show a little bit about the history of variance components. And some came, in fact, before ANOVA. So Lipka pointed out this paper from 1921. Later, many years later, we got Henderson proposing those Henderson 1, 2, and 3 when the data was still balanced. Few years later, there was that the early arisal of likelihood. And then we kind of had two paths of estimating variance components. The iterative path and the exact likelihood. And of course, and then we have the Remo methodology being more well established in 1970. And the paper from in fact, from the same author, Thompson, this guy, the same Thompson that proposed Remo, 3 years early, he proposed a method to handle non-orthogonal matrices. A big problem of ANOVA is that it handles very well data where you have everyone everywhere, the data is nice and round. But the first version of a ANOVA-like method that handled non-orthogonal matrices came slightly earlier than Remo. And it, by the way, had similar properties, unbiased, invariant, very nice. But, data, it seems that computation was not a problem. Statistics like the traditional Remo, and the gold standard became EM Remo, expectation maximization. Later on, average information from, again, Thompson, same dude. On the other side of people who do not have computing power, like they didn't in 1969, came a paper from Larry Schiffer in '86. They called it pseudo expectation. And a year later, another dude called Paul van Reyden just proposed some slight improvements to that, and he called the general purpose approximation to RAML. So basically, what I try to convey with that is that, there is a long story of variance components. Most of you have been coming to the right side, and the thing I'm going to present to you is the silver standard that is not as popular. It's the fast variation of the gold standard. So the idea of RAML, if we just do the first derivative, because who doesn't, right? The first derivative, as we all do when we have to solve our problems, it has the solution. It's called the beta hat, beta hat. And that's the derivation that comes from a technique called MIVQ, that if you iterate, you end up with the RAML. And the sneaky part is that if you just slash the inverse from both sides of the equation, you end up with something that does not have any C matrix, any V matrix. It's just straight up this Y tilde and the Z beta. Now, and then Van Reyden just proposed some intermediate solution. All right, so Schiffer said, let's get rid of V inverse, and Van Reyden said, let's just replace it by something similar, that he called the beta tilde. Then residual variance has never been a problem. It has always been very easy to compute. All right, and that's the solution we get from, either multivariate or univariate solution from the tilde hat. The beta tilde is estimated once with the Schiffer method or once every iteration with the Van Reyden method. But it's very simple. It's just beta prime beta. Again, it does not sound like much, but it really is very little. It doesn't take any memory to compute. You don't have to do traces of inverses, and that's a big limitation for big models. No C, no V, no left-hand side, no determinants, no inversions. It costs very little. All right, that math is very overwhelming. Can we simplify to something that's more intuitive? So if you can imagine, a genetic covariance from this method is basically you take phenotype A and predict from the markers from the second trait B plus the other way around. So it's basically, if you were to imagine, is how well A predicts B and B predicts A. So that will be a rough idea of how this covariance came to be. And then you can still, from those methods, get those genetic variance, heritability, correlations, all the cool stuff that we use in the day-to-day basis. All right, so I mentioned to you that we proposed some method that has estimates the marker effects one at a time. We found some variance components that can be fit with the Gauss-Seidel, and I'm just going to show you some simulations of how we assess this new approach that we proposed. For that, we check the computational efficiency, how fast it is to get this model in comparison to standard implementations. We check the accuracy to see how well we do in predictions. And we check our estimators, because sometimes you're running this mixed model not only to get the predictions, but also because you want to know the heritability, you want to know those correlations. Maybe what you care about is more the correlation and the heritability rather than the marker effect and the GBV itself. We ran with two data sets. One that we simulated 10 environments. In all the environments, we have all the lines. It's just a small data set, so 500, almost 600 individuals. And a bigger data set where each individual appears only once. So there's zero overlap across all the environments. In each environment, we have 500. Where's the pointer? I don't see the pointer. But in each environment, we have 500 individuals. And the total panel would be 5,000 lines. All right. One thing that I have to mention is that in some of the benchmarks in the incomplete data set, where you have zero overlap, we try to estimate the covariance components using RAML, and we were not able to. So our gold standard, when you don't have any overlap of individuals across environments, did not give any output for the covariance components. So you were able to use RAML as a benchmark in the more balanced data set, but in the bigger data set where there's no overlap, we were not able to get. And just earlier today, we were talking about sparse testing. So the second scenario we are testing is fully sparse because each individual has been observed only once in a different environment. So here's how long it took to fit the model. It's a model of 10 traits, 600 individuals, and 1,300 markers. ASRAML, the 4.2, which is claimed to be the faster one, took 272 seconds. AI-RAML, 109, Gibbs F3, 600, and the methods we proposed took 0.3 seconds, which is less than 200. All right. And the univariate running one at a time using our method was 0.23. So running univariate and multivariate was about the same. Here we just tested the elapsed time with bigger data sets, more traits, and up to 200 traits being fitted at once. And we're talking here about what they call the unstructured type of model. So we fitted 200 unstructured traits. It took us 80 minutes in the scenario with 4,300 individuals. Again, it can be much faster if you do some monkeying with the data. You can SVD the parameters. But on the very classical settings, that's how long it took. All right, so the method is faster. Is it equally accurate? So here we fitted a model with the true genetic value, the true value of the variance components and the Gauss-Seidel. Then we fitted RAML and the proposed methods. So what we see is that the overall trend is the same. We are always beating the univariate method. So the proposed method we are showing you guys here is capturing the G by E in a fraction of time with comparable accuracy. RAML, admittedly, did better in many scenarios. So the largest difference in bias of heritability is that when the heritability was high and the genetic correlation was low, our methods provided a little lower heritability than what RAML did. Bias in the negative way. 0.05. I suppose I could live with that. Another case here is when RAML did, so that's the bias of the genetic correlation. Again, we are capturing the genetic correlations. We may have a little higher standard error, but in this case, RAML was way more biased than the method we proposed. In one direction, RAML's bias was minus 0.08, and the other one was plus 0.07. So even though it's understandable we have RAML as a gold standard, but does not mean that the method is flawless. The estimators are hard. As you push more and more traits, it gets harder and harder to get covariance components. It's a tough thing to get. All right. And as for the precision, so precision is how far off you are with the estimator. Sorry, I just jumped out of that. So yes, there is a little more variability in your estimators to this method we are proposing. So they are unbiased, but they have a little less precision. That's the one trade-off we were not able to get rid of yet. Same thing with the genetic correlations, a little lower precision. So precision is like the variance of the estimator. And again, a little less precision. Right. That being said, if your data set is small, it's fine to use RAML because you can run RAML. But as you get more and more data, it gets harder and harder to run RAML, BGLR, you name it. And as you get more data, you get less bias and higher precision. So what I want to convey with this table is that as you jump from 250 to 3,000 observations, so as your data set becomes much larger, your coefficients all get unbiased. Meaning that if you have a data set that's large, you cannot even run with RAML, you can consider switching to a lighter solver. Because you probably have that data that's big enough to not be able to run with RAML in your computer. And here's a good solver for you. But if your data is tiny and you're not doing too many traits, it should be fine running with Remo. All right. I added a slide just with some precautions. What happens if you have too many replicated traits or fixed effects? You can bypass that. You can add a little bit of overhead. An important thing is our method is fast because we are not assuming correlated residuals. They can be modeled to a identity design matrix. So then you'd split shared residuals and independent residuals. If you have kernels, you can just SVD them or EVD them and do the same thing, solve with the Gauss-Seidel. And as you increase the number of traits and you start having 100, 200 traits, it's a little harder to get that variance-covariance matrix to invert, so we may need bending. Last disclosure is that if your data is perfectly balanced, you can do some monkeying with the data to get Remo to fit it very fast. So I just did some general recommendation. If your data is small enough that you can run Remo, knock yourself out. If you have 5 to 20 traits, you may want to start moving to Gibbs, that's more stable. As you get bigger data sets or many more traits, you probably want to consider our solver. And if you have thousands of traits, thousands of environment trait combinations, you can move to more specialized traits, which is the paper that we did not get accepted yet. All right. So as my conclusion is that those multivariate models, they are valuable, but they are, they have been computationally unfeasible to fit. We provided this estimator that, you use Gauss-Seidel to get the coefficients, use pseudo expectation to get the variances, and it can handle reasonably large regression models. And basically our recommendation is that, if you have a problem with Remo, be aware there are alternatives. And before I jump to the question, I just wanted to promote one more initiative. So right now there is an open competition from the Genomes to Field initiative. Please consider signing up. Basically, it's a very nice competition where you get some data from several environments, you get the genotypes, you get some environmental information, and they give you the genotypes and environmental information from 2024, and you have to predict this new environment. A lot of fun. If you guys win, you get $4,000 plus $1,200 in traveling to present your method in the MGC conference next year. It's, in the last competition, the first and second place were from Brazil. So that's, if that serves as an incentive. Sorry, that was my last slide. Thank you, guys.
We now have time for questions.
I think it's a simple question, just out of curiosity. Is there any intuition behind why the model progresses much faster using a randomized order of SNPs? Because I've seen that happens in some other areas of statistics, like random SVD, for example. Randomized SVD also works much faster. I don't know why it happens.
Yes, so we have a theory of why that is if you progress linearly, all those, and you hit, say, a QTL, the SNPs have a really high autocorrelation. So they are very collinear. And to spread out the effect of a QTL, it's going to take a bunch of iterations until, say that you have 10 markers that are fully in full LD. Eventually they would have all exactly the same effect. But if you always iterate from the left to right, from the left to right, from the left to right, it's going to take a long time until it evens out those effects. And genomic models are well known for this high collinearity between the markers. With the whole genome has LD with the neighbor markers, and has something to do with alternating the order by which you update the SNPs.
You mentioned about the big data set, and for me it's not very much clear what is a big data set. How many lines, observations, or something like that?
Right. Yeah, big can be subjective. depends on your computational capacity, right? So basically, if you just run your analysis on your laptop, and I do, doesn't take much to have a data set that you cannot run with GLR and ASTREMO anymore. These days, I like to think that models with more than 20 response variables are big, because that's the consensus capacity of a RAML estimator. Of course, here we have no issue to fit up to 100, 200, 300 traits. In terms of number of lines and SNPs, if you have too many more SNPs, you may want to do some SVD, something that has all the information, but you don't have to fit all the markers. And if you have too many lines, there are ways to get around with subsampling, lazy loading, and other tricks you can do it. But I would say that a large could be a million individuals genotyped with 100,000 SNPs. That would be big for any standard, I suppose. Those human data sets are reasonably large. They are fairly square. They have bunches of individuals and bunches of SNPs.
Any more questions?
Okay. I have one.
You, short one.
Yeah. So with this new methodology, how will the power of computational UWIF is necessary to run the analysis?
I mean, I can run in my phone. I chose. No kidding. It's like sometimes you can install Linux in your phone, and all those examples with 4,000 GEs, genotypes, and 5,000 markers, you can run in a split of a second.
Great. So nice.
You said that if you have non-overlapping genotypes with no text, you can't fit a REML? What will you need? At least one common tag, or?
So in one of the slides where I present the overlap, as you get more and more overlap, there you go. So, all right. So when I had zero overlap, REML set everything to zero. As soon as I got more records, REML, which here is in red, starts estimating something. And of course, as you get more and more overlap, estimators got better and better.
Okay. And this overlap can be either in environments or traits?
It has to be the same individual. Yeah.
What's the other factor? Environments or traits? Or?
So if the individual has only one record,
Okay.
you say that you have 20 individuals, and you have 10 in one environment and 10 in the other environment, and there are no overlap. So that's the case where REML cannot do anything for you.
Okay.
But if that one individual has been observed at least a few times or in a few locations, you should probably be fine. I mean, high standard error on that estimator, but you should be able to at least get something out of it. Okay. But the case where we're testing here is the extreme example of sparse testing, where each individual appears only once, only in one environment.
Any more questions?
Thank you, Alencar. So you can use same that they are great.
Oh boy. Can I? All right. I didn't want to get into the merit of it, but since you ask, so we fitted the model that prior we call it the pegs. Here we just call it multivariate, and we went as far as fitting 2,000 traits in 2,000 individuals, or 200 traits in 20,000 individuals, and that is the time in minutes. So in REML, we couldn't even pass the 10. As soon as we hit 50, that didn't go any further. And our most efficient method, it fitted 200,000 individuals in 200 traits in 5 minutes, or 2,000 individuals in 2,000 traits in 3 minutes. So we are really pushing the frontier of how much you can run. And we got some other stuff, like that's the genomes to field from the previous iteration. It's one of the case of studies we did, and we learned that not doing multivariate was better than doing multivariate. We saw that, like, if you just do a gblup across all the environments, you get as good a prediction as if you had like models for each specific environment, unless you were to use an XFA or heteroscedastic compound symmetry, which in the paper is described, but here it just looks out of context. But yeah, and here's the code of how I did the whole paper. 18 lines of code, amazing. I just simulate the genome, line 5, the correlations in line 6, the heritability in line 7, the phenotype is in line 8, and then I fitted the model. Like a bunch of models in line 12, 13, 14, 15. Yeah, but no more spoilers.
Thank you.
So, Professor Xavier, on behalf of the organizing community, we would like to express our sincere gratitude for your insightful presentation and for sharing your expertise with us today. As a token of our gratitude, we would like to offer a small gift to capture this moment with a photo.
Thank you very much, guys. It's a pleasure.